Hey there, welcome to another edition of Mr. Weis Solves an Old AP Problem. This time we are doing problem from 2008, number 2, which is kind of interesting. I'm going to read what the problem says. It says that concert tickets went on sale at noon, which corresponds to t equaling 0, and sold out within 9 hours. The number of people waiting in line to purchase the ticket at time t is modeled by a twice differentiable function L of t from t equals 0 to t equals 9. And they're not telling us what L of t is, but instead they're giving us the values of L of t at a couple of select points, a couple of select moments in time. So generally I like to get my bearing in problems like this, make sure I know what's going on. So for example, what do these numbers mean? 0, 1, 20. Well, this means that at time 0, which is noon, there are 120 people standing in line. At time 1, which would be 1 p.m., there are 156 people standing in line. So now interestingly, right, probably what's happening here, if you think about the real world, is these people are standing in line to buy tickets, and some people are getting their tickets and getting out of line, but as that's happening, there are also other people coming to stand in line. We have basically what I can see that's happening in the first hour here is it seems like more people got in line than ended up leaving, because after 1 hour we have 156 people still standing in line. You can see that at this would be 9 p.m. nobody's in line anymore, and the tickets are sold out basically. There's like an interesting thing that happens here at hour 4 p.m. it's like got lower, but it had been 176 people in line the hour before, and 3 hours later there's 150 people in line. So interesting, okay, interesting function. So the first part A says, use the data in the table to estimate the rate at which the number of people waiting in line was changing at 5:30 p.m. So it wants to know the rate at which the number of people waiting in line is changing at 5:30 p.m. So if you think about it, and basically this is the key thing, is realizing what it is asking you for in math language. What this wants is the rate of change of L at 5:30 p.m. We have another symbol for this. We want L prime at, now 5:30 p.m. would be 5.5. Now of course we can't get that exactly because we don't even know what it is at 5, but we make the estimate that this is the slope of the tangent line to L at 5.5. I suppose we should use a secant line that is using nearby points to try to estimate this. So I'm going to put a little squiggle symbol, and I'm going to say that this is probably approximately equal to 5.5 is right in the middle of 4 and 7, so it's probably in the middle of L of 7 minus L of 4. That's the change in the amount of people that were standing in line from the 7th hour to the 4th hour, divided by 7 minus 4. That's how many hours went by during that time. So this ends up equaling L of 7 is 150 minus L of 4 is 126 divided by 3, and that equals some number which you could use your calculator to figure out is 8 if you get out your calculator to do this. And I believe this isn't a calculator problem, so you're fully allowed to do that. Now importantly, we want to make sure that we understand what unit this is here, because this has meaning. This is a word problem. This is a real world situation. So this is the rate of change of people standing in the line. So this would be 8 people per hour. In other words, we estimate that at 5:30 p.m., the number of people who were coming on the line every hour was about 8 people. That every hour, at around 5:30 p.m., every hour that went by, we estimate that 8 new people were being added to the line. And that's the answer to part A. Okay, here we are with part B of the 2008 number 2, in which we're dealing with this function L of t that tells us the number of people who are standing in line to purchase concert tickets at any time t, where t is measured in hours and t equals 0 starts at noon. What part B asks us to do is it wants us to estimate the average number of people that were waiting in line during the first 4 hours of ticket sales. The average number of people who were waiting in line during the first 4 hours of ticket sales. So for example, I can see that at time 0 there were 120 people waiting in line. At time 1 there were 156 people. At time 3 there were 176. At time 4 there was 126. I would like to estimate the average. Now, one reasonable thing might be to do, if nobody told you anything, would just be to kind of average these numbers, but there's some strange thing that stops us from being able to do that. The fact that the time between 1 and 3 is longer than these other times means we aren't really thinking about, we don't actually know what's going on at all of these other times to be able to figure out what the real average is. What this problem is really asking us for is the average value of this L function over the first 4 hours. And we actually know what, and again, if we convert this into math, we actually know what that means. What problem B is asking us for actually is L avg, or maybe you guys wrote AVE, I don't know if you wrote L avg or L ave. This is the integral from 0 to 4 of L of t dt. This is us adding up all of the L values from 0 to 4, and then we divide by the length of that interval, so times 1/4. And so this is actually what we're going to estimate, and they actually give us a big hint here because they say use trapezoids to estimate with 3 subintervals to estimate the average number of people waiting in line over the first 4 hours. That's actually the way the problem reads. So that's what I'm going to do. I'm now going to use trapezoids to try to figure this out. So I'm going to estimate this integral here with trapezoids. Now here's a big warning. The trapezoid formula that you learned in class only holds if the intervals you're doing the trapezoid sum over are all of the same width, and that is not the case here, which means we cannot use that formula. We're going to actually have to calculate the areas of each one of these trapezoids. So let's get at it. We estimate, so I'm going to put an approximate sign because this is approximate. The 1/4 is just going to be hanging out in front here. I can't do anything about it. So now I'm going to do the first trapezoid. So remember how this basically works. Just a quick picture of what these trapezoids often look like. They end up looking something like this, where actually base 1 is the value you get when you plug the point in question into the function. So here we're going to be plugging in 0 into the function, and we're going to get this height, which is 120. Then I'm going to plug 1 into the function, and I'm going to get this height, which is 156. But these are actually the bases of the trapezoid that's been turned on its side. The height of the trapezoid is this length right here, which is the delta x. So in fact, that means that my first area, my first trapezoid, is just going to be the average of the 2 bases times the height. That's the formula for the trapezoids, for the area of a trapezoid. So it's going to be 120 plus 156 over 2 times 1. First trapezoid done. Second trapezoid is going to be the one that goes from time 1 to time 3. So that's going to be 156, that's plugging in 1, plus 176, that's plugging in 3, over 2, the average of the 2 bases, times the height, which is the width of this interval, which is 2. One more to go, plus the last trapezoid is from 3 to 4, and this is going to be 176 plus 126 over 2 times the width of this interval, which is 1. And I then get out my calculator to figure out what all this is. I'm just going to tell you that the answer ends up becoming 155.25. And again, it's worth noting, what does this actually mean? This is the average number of people that were waiting in line from over the first 4 hours. So this is people. This is people. We estimate, we're not 100% sure about this, but we estimate that within the first 4 hours, on average, there were about 155.25 people in line, based only on knowing these few values. 1, 2, 3, 4 values. We were able to make that estimate. Okay, here we are doing Part C of the 2008 number 2 AP Calculus BC exam. This one's a bit of a doozy. It's a real think question. There's not a lot of math that's actually going to happen here, but there's a lot of thoughtful stuff that has to happen, and you have to have some good writing to explain what you're thinking. All of this problem has had to do with this function, L of t, which is keeping track of the number of people, modeling the number of people that are waiting in line to get concert tickets at any time t, where t is measured in hours and t equals 0 is thought of as noon. The tickets sell out after the first 9 hours, so after at t of 9, which is at L of 9, which is at 9 p.m., there's nobody waiting in line. You're also told that the second derivative of this function definitely exists, though they only give us some values for the function L of t. It's not a terrible idea to even sketch a quick graph of this if you want, although the scale is a little bit weird and would be kind of hard to do. You'd only be able to plot these few points, but you would know that there's some kind of nice continuous and differentiable, in fact twice differentiable function that has to pass through all of these points, 0, 120, 1, 156, and so on. Doing so might help you to answer a few of the questions that you're being asked, including maybe this question, because Part C asks, what is the minimum number of times? What is the minimum number of times that L of t, L prime of t equals 0 on the interval from 0 to 9? What is the minimum number of times that the slope of the tangent line equals 0 on this time interval from 0 to 9? And like I said, if you tried to plot this thing and you plotted a few of these things, plot a few of these dots, you might start to note that, oh, well, the function looks like it has to be going up here from 120 to 156. There has to be, at least on average, the function has to be increasing. Look, maybe it's not increasing over this entire interval. Maybe it's doing all sorts of weird stuff. Maybe it goes up and then down. Maybe we have a bunch of places where L prime equals 0 in this interval, but I can't be sure of that. But I can be sure that on average this function is increasing over this interval. In other words, there has to be a point in this interval where L prime is positive. There has to be a point in this interval where L prime is positive. There has to be a point in this interval where L prime is negative. Ooh, that's interesting. Positive again, negative, negative. And it's in fact that argument that I'm going to end up making that's going to let me know that there are going to be 3 places, I think, where L prime has to be 0. So let me make that argument now. Here's what I would say. L of t, L prime of t is continuous. We know this because L double prime exists. L prime of t is continuous, and L prime of t exists. What that means is that the mean value theorem applies. So, the mean value theorem applies. Thus, by the mean value theorem, this is important, by the way. Noting that you're allowed to use the mean value theorem is important. Noting that the conditions that are necessary for the mean value theorem to hold are met should be noted. So by the mean value theorem, there is a point in the interval, I'm just going to say from 1 to 3, where L prime of, let's call a point, let's give it a name. We'll call it let's give it a name. We'll call it, there is a point C1 in 1 through 3 where L prime of C1 is positive. Why? Because L of 3 minus L of 1 over 3 minus 1, because L of 3 minus L of 1 over 3 minus 1 is positive. In fact, we could actually go much more than this. We could say there is a point C in the interval from 1 to 3 where L prime of C equals exactly what that number is. That number being 20 divided by 2, I think. 20 divided by 2, which is 10. In fact, I could say more. In fact, 10. Cool. Similarly, there is a point C2 in the interval from 3 to 4 where L prime of C2 is negative. By the same argument. In fact, I could say exactly what the negative number is. It's 126 minus 176, so I think that's negative 50 over 1. So in fact, negative 50. But let's think about this. L prime itself is definitely a continuous function. So not only does the mean value theorem apply to L of t, but the intermediate value theorem applies to L prime of t. So I'm going to add that, and IVT applies to L prime of t. So by the intermediate value theorem, there must be a place between C1 and C2 where L prime equals 0. So by the intermediate value theorem, there is a place, a point in C1 comma C2 where L prime equals, we can even give this point a name. Let's give this a name. Let's call it point B1, where L prime of B1 equals 0 by the intermediate value theorem. So I just found 1, 0 of L prime. I'm now going to make this argument a couple more times. I'm going to say that, so I'm going to say between 4 and 7, there exists a point C3 where L prime is positive. Therefore, since L prime of C2 is less than 0 and L prime of C3 is bigger than 0, there's some point between C2 and C3 where L prime equals 0. We just found our second point. Then I'm going to do it again. From 7 to 8, there is a point where L prime is negative. We can call that point C4. But L prime of C3 was positive and L prime of C4 was negative, so there must be a point in between C3 and C4 where L prime equals 0. This gives me a total of 3 points where the derivative equals 0, and that would be the end of this problem. So there's a fair amount still to write here, and that I don't feel like doing, but that would be my answer to this question. Okay, so here we are on the last part of the 2008 number 2 AP Calculus BC exam. This one abandons the function that we had been looking at previously with the function that told us the number of people that were waiting in line to get tickets for this concert, and instead tells us that they have this other function which they call R of t. And R of t equals, let me put it in their words, R of t equals the rate at which the tickets are sold in tickets per hour. So this is the rate at which tickets are sold measured in tickets per hour. And this time, instead of giving us just a couple of points, they actually tell us what this function is. And this function is 550t times e to the negative t over 2. So again, not a bad idea to get your bearings for this. And I assume here that t is the same as before. T is measured in hours, where t equals 0, it corresponds to noon. So again, it's not a bad idea to get your number. So what this means is that what's r of 0? R of 0 then would just end up being, 0. In other words, at noon, there are no tickets being sold per hour. However, at 1 p.m., there are approximately, we'd have to figure out what this is, but I don't know, just a very rough estimate here. This is 550 times 1 e to the negative 1/2. So that's like the square root of 2, 1 point something in the denominator. I don't know. I had to get my calculator, but this is under 500 tickets. Under 500 tickets are being sold per hour at 1 p.m. This would be like an instantaneous rate, right, though? So and this would just be an estimate of how many are being sold per hour at that moment in time. So, cool. What this problem wants us to do is figure out, based on this model, how many tickets were sold by 3 p.m. How many tickets sold by 3 p.m.? Okay, so this is a very standard situation where we have a function that's telling us a rate, and we don't want the rate, we want the actual total number that are sold. We want the total number. So what this problem is asking us for, if you convert it into math, what this problem essentially is asking us for is, what is the integral? So the answer is, what is the integral from 0 to 3, because that's the first 3 hours, of r of t dt. And you have a calculator for this, so I would use the calculator to figure this out. It's an interesting question to wonder if this is a integral that you could do by hand. I think it's possible. It's possible this is an integral that you can do by hand. For example, you could, I think if you did integration by parts on this, it's possible that you'd be able to compute this by hand. But I wouldn't really bother. I would get out the calculator and get it done. And I will do that for you and show you with some of the work. But the answer ends up being approximately 972.784 tickets. I think the big idea of this problem is the concept of when you're given a rate, a function that tells you a rate, what does the definite integral of that function end up telling you? It gets rid of the rate and turns it into whatever the numerator is. In this case, it's tickets per hour. There's a lot of ways of thinking about this, and a lot of ways that you maybe have learned it. One thing you could do to help you realize this, like the way you probably learned it in your physics class perhaps, where you were doing velocity and the integral of velocity. Velocity is a rate. The integral of velocity, the definite integral velocity, is displacement. That is basically what's happening here. If we were to graph this rate function, on this axis would be hours, and we'd be graphing tickets per hour, and we'd be finding the area under this tickets per hour function. And that area ends up being, on the y-axis, you're multiplying tickets per hour. By hours, you're getting tickets. You're getting the total number of tickets sold. Now, this in fact is the total number of tickets sold because this function r of t here is always positive, okay? There's no negative rates being sold in tickets, and that should make sense because I guess what it would mean for there to be negative, for the rate to be negative tickets per second, which would mean that people are returning some of the tickets, and that's not happening here. So this is, you might think this is the total number of tickets sold. This is kind of like total distance because the function itself is always positive. And I hope that makes some good sense.